Hello, everyone. This is Veysel from Johnson Labs, Head of Data Science. I'm leading the healthcare NLP team at Johnson Labs for the last few years. And today, in this session, in this keynote for the NLP Summit, I'm going to present some cool benchmarks and updates from our site, which I can just title it like Beyond Q&A and like multifaceted evaluation of our upcoming brand new medical chatbot. Which I hope that you will all like a lot after this presentation. So let's get started. So as you know, for the last 3 years, especially for the last 1 year, let's say, with the advent of ChatGPT, when it is live, like generally available in October, I guess, last year, October. Since then, there are there were already GPT-3, all the other GPT families, and then GPT variants to open source version. But for the last 1 year, as you know, especially the instruction fine-tuned of LLMs are hype and taking the world by storm. So every day there's a new model being released. Today is the end of the September. When you listen to this recording, there might be new LLMs out there as well. But the last one, the last most capable ones, as you might know, after GPT-4, there are open source version of like Llama 2, and Mistral is released like a few days ago. So we have two family actually, open source and closed source. So and not all the open source versions are commercially available, but most of the open source right now are as good as GPT 3.5 itself. So, and since GPT 3.5 and 4, people started to test the capabilities of GPT on the medical challenge problems to see if we can solve our problems with these LLMs. So since GPT-4 is kind of state of the art right now, everyone is using this as a sometimes human level accuracy, sometimes just rather than annotate from scratch for the ground truth, they use GPT-4 or 3.4 as a ground truth annotation and then evaluate their model against this. But even GPT-4 itself, according to the recent papers, are not hitting the highest scores with zero shot. Like zero shot means that if you give it no instruction, if you just ask questions blindly, it is zero shot without any instruction. The accuracy of GPT 3.5 zero shot capability is like on MedQA, it's like 40%, but in the GPT-4, when you do 5 shot means that you ask questions, similar question, and then you get answer, you ask another question, and then you get answer, and you give answer, by the way, which means that you kind of direct the LLM to let it give you what you expect to have. So that's why people evaluate these models with 5 shot, zero shot, and also across different models. For example, Palm is a model released by Google, GPT is released by OpenAI. Anyway, these are the benchmarks on the medical challenge problems. But these are not the real world use cases, right? So no one is doing MedQA, no one is doing Pubmed Q&A, and then you can just easily overfit. And we are not even sure that GPTs or all the other LLMs haven't seen these data sets even before, because LLMs are quite capable of even memorizing from one single example. So that's usually we only fine-tune one hypo just to get a nice accuracy right now. And there's a peril over there, there's a risk over there that even GPT-4 still answers 40% of the questions incorrectly according to some truthful Q&A benchmark. Even with human feedback, reinforcement learning, and some even few shot, it is still not able to answer 40% of the questions correctly. So that's quite a risk, because you may never know when it is correct or not in the clinical settings, and it's a high risk. Then RAG comes to rescue, right? So because you cannot just rely on LLM's own memory, own knowledge, own closed book capabilities, right? Because if you have a document to guide you through, and if you want to find an answer out of these documents just by sticking to these documents, you need something else which RAG offers over there. It's called retrieval augmented generation. It's the combination of your own documents or some open source documents plus LLMs as an agent. LLMs job in RAG, maybe I should explain from scratch. What we do with retrieval augmented generation is that you have a set of documents. It would be Pubmed articles, or it would be your own in-house documents that you want to ask a question. right? That you want to ask a question, specific question out of 1 million PubMed articles, let's say. What RAG does, like RAG, in what we do in RAG architectures over there is that we split them into chunks, we get the embeddings of them, and then write to the vector DB. Then when we ask a question, like what's a cystic fibrosis or something, we get the embeddings using the same embeddings model. We get the embeddings, send it to the vector DB. Vector DB return top k. It could be 5. Usually people use 3 or 5. Top n number of similar splits, and then over there we get all these splits and then call them content. We send it to the LLM. We say that respond to the question based on the content, like these relevant documents returned by the vector DB. Answer my question, right? So LLM's job over there is to follow your instruction, finding the answer out of the splits that is returned by the vector DB. So LLM's job over there is kind of limited only to finding the answer given the content splits returned by the vector DB. So it is not doing hallucination, we hope. But sometimes, because this is also, we are also using prompt template, right? So if you do not pay attention to your prompt template and the questions are too straightforward, LLMs tend to answer it directly without even checking the splits that we feed into. That's why we are being so precise, specific, and descriptive when we write our prompts in RAG architectures. Otherwise, LLM could even make up some answers without even using the splits you feed into the LLM part. So we understood right now. Let's say we understood what RAG does over there, right? Now let's see the components of RAG one by one, because I'm going to explain how we attack each one of them, right? We have 5 stages in RAG architecture. Source documents, as I explained. Document splitting, because we need to split the documents into chunks, like some sizable chunks or splits. We need to get the embeddings of each chunk, each split. Then we need to write them into a vector DB, and then the last stage is LLM. So in RAG, we have 5 stages, actually, 5 components. In each component, there are some perils, there are some risks, and there are some opportunities lie, actually. For example, source documents. If you do pre-processing, where you need to do pre-processing very well, sometimes maybe the documents are PDF or some scanned images, right? You need to pay attention to OCR over there. You need to do the basic cleaning. If you don't do this, the results are black and white, right? So the results might differ. So if you don't pay attention your pre-processing step, you may end up with a different results, and then you may try to tune the wrong part of RAG rather than to go back and then do the simple pre-processing. The second important part of source document is metadata extraction, because you can augment your vector DB with some metadata that you can extract from the document. It could be named entities, it could be just the other names or keywords, or the title of the documents, or the type of the documents could even be a metadata in RAG architecture that you can leverage later on while answering the question. And then the last step is feature engineering, which means that you shouldn't blindly take the documents and then split. You need to understand if there's a table, you may need to use table understanding over there. If there are chart, you may need to get some text description of the chart. You may need to sometimes do summarization of the source documents so that you can reduce the size of the embeddings and vector DB finally. These are all the steps that you can do, that you can add something new into this RAG rather than using default pipeline. That's why in our benchmarks, which I'm going to cover today, we used default pipeline that everyone is using, Haystack, LangChain, and we did some things at each step that you see over there. For example, document splitting, there are different document splitting strategies. It could be content-wise, it could be section-wise, paragraph-wise. You can change the max chunk size. This is becoming, like, as you see, with the advent of LLM, right now we are not trying to change the architecture of the deep, like a neural network, right? We are kind of changing all these techniques. We are treating them as a hyperparameter right now. So we are building a product around these LLMs right now by playing with these knobs that is easy to manipulate, actually, and easy to understand, because as a human, as a developer, right? So rather than playing with the neural network architecture that you could see the results sometimes very late like after training days, 4 days. But here, when you play with these techniques, you can get instant feedbacks, results, outcomes, so that you can change and try with different alternatives. So in the split embeddings model, like the name of the embeddings also matter. Like you are you going to E5 or MPNet or OpenAI embeddings, right? There's a leaderboard for this MTEB, they call it. So it's like a massive text embeddings leaderboard. That right now, surprisingly, OpenAI text embeddings, most of the people using that, but it is right now in the ranking like 12 or 17, I guess. So the best one out there is right now open source versions. You can play with the different size of the same embedding, like E5, base or large, and you need to pay attention to if this split embeddings model can be used at scale rather than just a few hundred splits, right? So these are all the techniques that you can play with and make a difference in your RAG architectures that people usually ignore and just use the default pipelines. So in the vector DB, there are different retrieval strategies, different post-processing, re-ranking, filtering, and when it comes to production-ready RAG architectures, you need to know the embeddings model, and then vector DB that you pick over there needs to scale and needs to be production-ready. It's not just like a chroma or quadrant that might fall. They might break up when you feed millions of documents, right? So that's why there are some scalable options over there, like Elastic or some other open source alternatives. And then the last stage is LLM. LLM's role over there is small, as I explained before, because it's only trying to answer the question given the contents. But model performance also matters over there. Why? Maybe because it needs to be able to follow your instructions. Otherwise, it may try to make like it might fail to cite the resources, or if the questions are too straightforward, and if there's a black hole in your prompt, the LLM can just try to directly answer it without even checking the content. So the first issue with the RAG is, since we understand each step, right? The first issue with the RAG is right now, it returns top K, right? When you ask a question, you get the embeddings of the question and sending to the vector DB, and it returns top K result. Then top K could be if there is a millions of chunks, because if you have a 1 million document, there is probably 10 million chunks over there, like a splits over there, because we split each document. If it is multiple pages, maybe you will have 100 million different splits. So when vector DB return top 3, there might be many other top 3 combinations that you may not be aware of. Maybe it's much better when it gets 3, like this 3, right? Of course, it is doing some similarity, KNN, but when you have a large chunks and get the embeddings and then the question embeddings, when you do the similarity, it's not clicking very well because there's a question form here and there's a plain paragraph here. When you get a similarity, it's not that straightforward. That is why people are using also some query expansion, query post-processing as well to be able to get a better representation of the query and splits. So it's basically you ask this question, it's just if this paragraph is over there in the DB, it thinks that it is the closest one and it returns, and you get n number of this kind of paragraphs. LLM doesn't see the other part, by the way, and then you club them together and then send it to LLM and ask that given the context, it will answer my question. Perfect. So, but there's a big risk over there, as I said, that we don't know if there's a better alternative over there in terms of top K, right? Because everything depends on top K. The other part is embeddings at scale, another risk in RAG, because you play with like 100 document, 1000 document. I have seen many webinars and YouTube tutorials that people are playing with like 10 PDF documents or 100 TXT files, etc. But if you are going to do this in production, you will probably parse millions of documents, and then there are tons of different options when you need to pick the embeddings model. So in the embeddings model, if you try to split 1 million, if you try to get an embeddings for the 1 million split, it will take like days. So if you don't have a proper embeddings framework over there, you may need to iterate faster. You may need to wait again and again. Just like before, like a pre-GPU era, you need to wait like weeks to get a proper results from your computer vision models. So here Spark NLP comes to rescue, right? Spark NLP with 5.0, it introduced the Onyx optimized and plain version of all these embeddings that Hugging Face also offers. On the left-hand side, you see the MTB leaderboard, and as you see, 17, like the OpenAI text embedding that most of the people use through the API is 17 in this ranking. Just today, I just checked, there's another Sionic embeddings, which I haven't heard before, but we will probably hear more in the next few days. But like people are usually GT, E5, and instructor embeddings are popular nowadays. Based on their dimension and size, you pick one. And then if you want to iterate faster, most of the people use Hugging Face over there, right? But when you want to do this with 100 million ciblets, this is what the difference compared to Spark NLP and Hugging Face or any other PyTorch-based embeddings collection. So for 1000 document, right? So Spark NLP is like blue bar represents Spark NLP versus Hugging Face, like the size of like how like improvement, size of improvement, like 2 times better. And this is the quantized version of Spark NLP versus Hugging Face, so which means that it is 3 times faster when it's compared to Hugging Face. So when you scale the documents, this difference, especially on the Onyx side, gets bigger and bigger. Right? For example, here for the 50,000 document in ciblets, the Spark NLP quantized version is 7 times faster than Hugging Face and 4 times faster than without even quantization. So which means that if you want to do this at scale, even on one single machine, it is still much faster if you use Spark NLP so that you can iterate faster. If you have clusters, Spark cluster, because Spark NLP is sitting on the shoulder of Spark itself, so it can scale natively, right, over Spark clusters. So you can have single worker, like single node or multi-node and n number of workers. If you have 100 million ciblets and if you have a nice big Spark cluster, you will have all these big differences that you see here. You see the differences, for example, for the 1 million documents, if I have 16 workers, it is like 180 seconds, like 3 minutes, right? In 3 minutes, I'm able to get an embedding through Spark NLP over a Spark cluster for 1 million documents. So if you want to do the same with any other non-Spark based embeddings collection, it will probably take like hours. Okay, so this is the benefit of picking the right embeddings, especially in Spark NLP. Then here's our benchmark. Because we develop some RAG architecture and then we label, like we are going to offer this behind Medical Chatbot product, which I'm going to explain in a bit as well. So over there in Medical Chatbot, we have multiple modules. One of them is RAG, that you can talk to your own documents versus on in-house documents as well, like or Pubmed pre-built knowledge bases or MedArxiv, clinical trials, etc. So we did the benchmarks because since the beginning, I've been saying that people are not paying attention on these stages of RAG, and then they just pick the default LangChain and haystack pipelines, right? So when you do the default, there is a library over there called RAGAX that is evaluating the RAG over 5 to 6 different benchmarks, metrics, let's say. We tested this over 1,400 Pubmed articles related to diabetes. So we created 1,400 Pubmed articles. Our physician annotators review all of them to make sure that they are good enough to include into a knowledge base. And then we use all on PNet embeddings, and then we use FIS as a vector DB. It doesn't matter which vector DB you use. It only matters when you move into production, by the way. But we did some experiments with Elastic, FIS, Quadrant, Chroma, and we see that the differences are very small when you are doing just 1,000 documents, just some iteration. So these are nice options when it comes to do some in-memory vector DBs. So then we did RAG benchmark. We built a RAG pipeline, as I explained in the previous slides. And then we tested over 3 different criteria. I'm going to present 3 criteria. The first one is faithfulness, which is about the generation capability of RAG, which is about LLM part of the RAG. And context recall and context relevancy, which is about retrieval capability. It's all about vector DB and embeddings part of RAG architecture. So according to this test, we created some ground truth. We created 200 questions, by physicians, and then we generated answers for 200 questions by using this 1400 articles, Pubmed articles. Of course, we use only the benchmarks, like abstracts, conclusion, and discussion sections to be able to create the ground truths. Anyway, the plain one, the default version, without doing any tuning, we just picked it. Embeddings, we didn't pay attention how to split, we didn't do any post-processing, and the context relevancy is like less than 10%. Context relevancy is a ratio between the sentences required versus the total sentence in the context. So which means that there are some sentences within the splits that are returned and they are usually useless, which means that the smaller your splits, the better. But sometimes people reduce the size of the vector DB, they just use it plainly. So we improved that a bit, and then in our improved RAG architecture, it is around 17%, which is still way better than 10%, right? So the context recall is ability of the retriever to retrieve all the necessary information to answer the question. For example, if each statement from ground truth can be found in the retrieved context, the context recall is high. So that's why our improved RAG architecture is doing 55 over there, while the plain one is doing like 40%. So we have 15% jump over there. So in total, we have around like 20 versus 40% in the average, because RAG score is more than these 3 metrics, by the way. So that's why we kind of, in average, we get like 2 times, like we improve the metrics by 20%, which is like 2 times better than the plain one. The plain one is without tuning anything. RAG, our own architecture is like context, meta-augmented plus post-processing technique, which I'm going to explain in another presentation, not here. We get around 2 times better results compared to the plain one. So the last one is faithfulness. Faithfulness is the information consistency, which is all about the LLM. So maybe if it is making up or not. As you see in our improved prompting, we get around like 15% better results compared to the plain one. Okay, so here's our benchmarks. But no LLM or RAG application can answer these questions, right, alone. So that's why we are also working on right now, feeding all your documents and then parsing through healthcare NLP pipelines, creating some tabular databases like SQL databases or knowledge graphs, and then using LLM as an agent so that you can ask questions directly, so that you can find this kind of extra across document relationships as well, which is going to be part of the Medical Chatbot product. So this is what we are going to achieve in our GSL Medical Chatbot product. It's going to be able to process your own in-house documents, your tabular data. It can generate insights from the documents that you are talking to without using LLMs its own power. It's going to use healthcare NLP through agents, and it's going to run on your on-prem, which means that you will have everything on your on-prem without relying on any internet connection. You will even have the LLM itself in your on-prem. So there's a short video that I would like to show you. So this is right now, I'm asking a question to Pubmed knowledge base, and it is even citing the items one by one. So it is returning a one single answer, and it's also telling me where that information comes from. Then I keep asking questions. Because this is a hard problem, by the way. While doing RAG, you need to use LLM itself by skipping RAG framework. You need to hit LLM direct if you have a follow-up question, given the content, given the answer returned in the previous stage. So that's why we did some like a fine-tuning and then prompt stuff over there, so that we could be able to keep up with the conversation with RAG architecture by itself, so that it can cite the resources, no hallucination. You can do this with your own documents as well. I think we are at the top of the hour, so I have more stuff to show, but I will probably skip them. This chatbot product will be generally available on-prem deployments by the end of 2023. And then we will share more information, more updates about this product in the upcoming weeks. Please stay tuned. And then I will share the presentation as well after this. So there's so much things that I want to share as well, like when to pick RAG versus fine-tuning, which I'm not going to cover, but long story short, most cases favor RAG. So RAG is an important architecture that nowadays everyone is using. I hope you enjoy. Thank you very much for listening to me.